Let's talk about something you've probably used a million times, a thermometer. Seems pretty simple, right? You stick it in something, you wait a second, and you get a number. But what if I told you that this simple little act relies on a law of the universe so fundamental, so important, that scientists actually had to go back and add it in as a prequel?
I mean, really think about that for a second. When you put a thermometer in, say, a hot cup of coffee, how does it know the coffee's temperature? The reading you see, that's the temperature of the liquid or the sensor inside the thermometer. It's only touching itself. So how on earth can it tell you the temperature of the coffee? It feels like it should be obvious, but the answer is what makes science possible.
And this gets us to a really core problem, a fundamental question about temperature itself. Before we can even begin to talk about heat or energy or engines, we have to solve this puzzle of measurement. How do we know, for sure, that two different things are actually at the same temperature?
You see, this isn't just some clever bit of engineering. For any thermometer anywhere to work reliably, there has to be a basic, bedrock rule of logic that's literally hardwired into the fabric of the universe, a kind of cosmic, if this, then that, guarantee.
So what is this universal rule? Oh, I love this part, because it's just so simple and so elegant, and it's the key that unlocks this whole mystery. It's the reason your thermometer isn't just making a wild guess.
Okay, so take a look at this. I know, it looks a little abstract, right? Just a few boxes labeled A, B, and C. But believe me, everything we need to understand how temperature works is hiding right here in this one simple idea.
All right, let's break this down, because the logic is just beautiful. Imagine you take object A and you touch it to object C. You let them sit for a while until they reach the same temperature. Cool. Now you take object B and you do the exact same thing with object C. They also end up at the same temperature. Here's the kicker. A and B must now be at the same temperature as each other, even if they've never, ever been in the same room. C is the go-between, the universal translator for temperature.
Now, there's a sciencey term for this state of being at the same temperature. It's called thermal equilibrium. It's a really crucial concept. It just means that things have balanced out and heat has stopped flowing between them. They're on the same page, temperature-wise.
So, let's bring this all back to our coffee cup. System A, that's your coffee. System C, that's the thermometer you stick in it. They hang out until they reach thermal equilibrium. So now the coffee is at the same temperature as the thermometer. And what are you, System B? You're the one looking at the reading on that thermometer. And that reading is, of course, in equilibrium with the thermometer itself. So if the coffee equals the thermometer, and your reading equals the thermometer, then voila, the coffee's temperature has to equal your reading. It's a perfect chain of logic.
This incredibly simple, almost common sense rule has a proper name, and its name tells a really funny story about how scientists sometimes figure things out, a little bit out of order. It's called the Zeroth Law of Thermodynamics. Yeah, you heard that right, Zeroth. It's the law that makes the whole idea of temperature a real measurable thing. It's basically the law of the middleman.
Which, of course, brings up the question, why Zeroth? I mean, we've all heard of the first and second laws of thermodynamics. Why not just call this the third law? Why go all the way back to zero? Did they just forget about it the first time around?
Well, yeah, they kind of did. It's a fantastic bit of science history. See, the first and second laws, which deal with big ideas like energy and entropy, were established way back in the 1850s. It was only much later that physicists took a step back and realized, whoa, wait a minute. They had built this entire beautiful structure of thermodynamics without ever formally defining its most basic ingredient, temperature. So when the law of equilibrium was finally written down in the 1930s, they couldn't just call it the third law. It was way more fundamental than that. It had to come before number one. So they gave it the slightly weird but perfectly logical name, the Zeroth Law.
And this isn't just a quirky little footnote in a textbook. The implications of this law are absolutely massive. Seriously, it's not an exaggeration to say that our entire technological world is built on it.
Just think about it for a second. Without the Zeroth Law, temperature is just a feeling. Hot and cold are just opinions. You couldn't build a car engine, a power plant, a refrigerator, anything, because you'd have no reliable way to measure and compare temperatures. But with the Zeroth Law, temperature becomes a real, universal, measurable property of the universe. It's what allows us to build everything.
This quote just nails it. The Zeroth Law isn't just another brick in the wall of science. Nope. It is the concrete foundation that the whole building rests on. You take it away, and the whole thing comes crashing down. It's that important.
So here's the bottom line. The next time you check your oven or take your own temperature, just remember what you're really seeing. You're watching a profound cosmic law in action. A simple little piece of logic, if A equals C and B equals C, then A must equal B, is what gives us the power to measure and understand our incredibly complex world.
And that just leaves us with one last thought. This law was hiding in plain sight for the better part of a century, completely taken for granted because it just seems so obvious. It really makes you wonder, doesn't it? What other simple, fundamental rules are out there, secretly running our world, just waiting for us to stop and finally notice them?